Hello, this is Yue Kuang, and I've been working on the cancer detection in gigapixel pathology images as my final project. Let's start with a brief introduction of the background of our project. In clinical pathology, human tissue samples are most often collected during surgery or via biopsy. They are further processed in order to make glass slides and be examined through a microscope by a medical doctor specialized in detecting and characterizing diseases on a cellular level. However, problems exist. The tissue samples are volumes, and each image is high resolution, while the expertise is rare. And also, the process can be fatigued and mistakes will happen. So, the goal of our project is to develop a tool to assist the physicians. Given a collection of training data, we will develop a model that outputs a heat map showing regions of a biopsy image likely to contain cancer. Since the images have really high resolution, it took several minutes for our model to make predictions. So for now, I'd like to first kick off our demo before introducing more details about the project. As we can see here, in the demo, we will load the trained version of our best model and make prediction on one of the test images, which is slide number 78. We have uploaded our trained model on the disk here, and also to save time, we also have downloaded the test image. For now, I will just click Run All, and we will come back later to see the results of our demo. Okay, so now let's continue with the details of our project. We choose the dataset Camelon, which contains 400 whole slide images collected independently from 2 medical centers in the Netherlands. It gives us slide level annotations. Our project will use a subset of it. We decide to use sliding windows of dimension 128 on level 3 resolution slides. We treat the problems as a binary classification and predict whether each sliding window contains tumor tissues. As we can see in the table in the bottom right here, we make a statistic of the number of tumor windows in each slide, and based on it, we choose the training, validation, and test sets. For efficiency, we ignore the windows that has tissue percentage less than 50%. And we did not include the slide 110 because it has non-exhaustive pixel level annotations. What's more, since the data distribution is unbalanced, which means there is much more normal windows than tumor windows, we choose equal number of normal and tumor windows from each slide to give us a balanced dataset. In total, we have 1,622 training windows and 162 validation windows. And we have slides 78, 91, 101 as our test slides. We decided to use the patch-based approach, which was proposed by Liu et al. To make the decision on a 129-dimension window in level 3, we use its surrounding contexts as multi-inputs to the model. As you can see here, we extract the surrounding contexts of size 299 from level 3, 4, 5 for each data point. Here is our model architecture. It is a multi-scale model which takes 3 299-dimension input patches at different scales. The inputs are passed through 3 independent models, which can be large pre-trained models like Inception and DenseNet, or a self-built CNN. The outputs are concatenated and then passed through a fully connected layer to generate the final output. Finally, we make the prediction on the center 128-dimension block of the original level 3 input. Here's a little more details for our training process. For the pre-trained models, we choose Inception v3 and DenseNet, and we first perform transfer learning, where we freeze all the original layers for pre-trained models and only set the newly added fully connected layer as trainable. We train for 6 epochs. And after that, we perform fine-tuning, where we unfreeze the top 2 blocks of the pre-trained models and train for 5 epochs. While on the other hand, for self-built CNN models, we train for 15 epochs with RMS prop optimizer with learning rate 0.001. Let's take a look at our model's performances on the test set. We choose several metrics, including true positive, false negative, false positive, true negative rates, F1 score, accuracy, and AUC score. Since we are doing cancer detection, we should take false negative seriously, since we don't want to predict a tumor window as a normal one. From the table, we can observe that the CNN model achieves 0 false negative rate. However, after a second look, we found that it is just because it failed to learn a pattern and simply predict all the windows as positive. It may be due to the problem of our small dataset size and overfitting. So we need help from the large pre-trained models. Both Inception and DenseNet gives us satisfying results, and we can see that DenseNet outperforms the Inception v3, gives us the best performance. It achieves high AUC score and F1 scores and a low false negative rate. Here is a visualization of the predictions on our test set made by the 3 different models we experimented with. The dark area indicates the real tumor locations, and the small red blocks are our patchwise predictions for each sliding window. We can see that both pre-trained models gives us a good result, and our best model can almost detect all the tumor locations with small mistakes. So here is a conclusion of our project. We implemented multi-scale deep learning models for cancer detection in Gigapixel pathology images. Our model achieves satisfying results and can detect most tumor locations with small mistakes. We can achieve an AUC score at 0.874. And we also found that the pre-trained models can increase convergence rate, the training speed, and help us with the small dataset, particularly for our problem. So now we can go back to our demo. Here we can see that our model have finished making predictions on the number 78 slide. And here is the evaluation for our model. So next, I'd like to give you a walkthrough for our code. We start with several helper functions here, like read slides, find tissue pixels, and we have also write helper functions, which help us to extract multi-scale windows that center at the same region. Here is the dataset preparation part. Here is the number of slides that we use for training, validation, and test set. And here is a helper function for us to prepare the data. We first download the slide image tumor mask, and here we move a sliding window with dimension 128 through each of our slide. We find the label based on tumor mask. We extract the input to our models here. And in this way, we can build our training and validation datasets. Here is an example of one of our data points from the training set. You can see that it's from level 3, level 4, and level 5, which gives us inputs centered at the same region while has different resolutions. They all have dimension 299. We upload our prepared dataset onto the GCP bucket, so in the future we can make use of it. We set the batch size as 2 to prevent the memory issues, and we create a dataset with TensorFlow helper functions. So here is our training part. First is our inception model. You can see here that we get 3 independent inception models, and we freeze their layers at first for transfer learning. We have 3 image inputs, and we first pre-process them and pass through different inception models. We get the encoded images and concatenate them, then pass through a fully connected layer to get our final output. Here is a plot of the architecture of our model. Next, we just compile the model and training it. We will save the model weights when we get the highest validation performance. And next, we will unfreeze the top 2 inceptional model blocks to perform a fine-tuning. We compile the model with a much smaller learning rate, and similarly, the training process is here. After that is the visualization and evaluation part. We remember the ground truth and prediction values for each patch, which can be used for our evaluation at last. Here is an example for image 91. We download the slide and we use sliding windows to make predictions on each 128 dimension block. And we label the block as tumor if the output is larger than 0.5. Here is a visualization, and we can do the same thing to the other two images in the test set. Finally, we will perform evaluation where we calculate AUC score, the true, false, negative, positive rates, F1 score, and accuracy. And for the rest of our notebook, we do the same thing to our DenseNet architecture and also on our self-built CNN model. That's it for our project. Thanks for your attention.